Hi, welcome back. Now I want to show you something that at least I found very surprising when I first saw it, which is about the relationship between adjunctions and monads. So hopefully you remember monads from last week. So let's see, if we start with an adjunction, so the data for this was that we had some category C, right, and some category D, and a functor F from one to the other, and the functor G going the other way, and we said that F was left adjoint to G if morphisms of the form f of x to b are the same thing as morphisms from x to g of b, where by the same thing we mean that we can turn one to the other and the other to the first one in such a way that if we make a round trip, then it's the identity, and similarly if we make a round trip the other way. Right. So that's what it means for f to be left adjoint to g. And we also had the concept of a monad. So this was always for an endofunctor, right? So from C to C, such that there was a return which had this type and a join which had this type. Right. So now I'm going to show you something very surprising about the composite f to g. So this composite is an endofunctor on C, right? And we're going to see that this in fact is going to be a monad. So how do we do that? Well, we always have this relationship between these morphisms in the different categories, right? So we do the trick that category theorists love, which is to instantiate B to be something so that we can put the identity at the top and similarly at the bottom later. So if we take B to be f of x, then we certainly have the identity at the top from f of x to f of x, right? Which means that if we apply 2 to it, then we get 2 of the identity, which goes from x to g of f of x, right? Okay, so that looks a lot like this return over here. Interesting. Right, so what if we take x to be g of b, and we also take b to be f of x, so this is g of f of x, right? Well, then we certainly have g of f of x to g of f of x at the bottom, and we certainly have the identity there. So just move it up a bit. So if we apply from to that, then we get something from f of g of f of x to b, which is f of x, right? So that's from of id. Okay, so that doesn't quite look like what we want, but now we can apply the functor g to this morphism, in which case we get something from g of the domain to g of the codomain, right? And now the magic happens, because here we have gf gf to gf, and similarly here we have id of x to gf of x, right? So this is the type of our return, and this thing here is the type of our join. So in fact, if f is the left adjoint of G, then G composed with f is a monad, right? Which is kind of amazing, because why should these two concepts have anything to do with each other, right? So it's very nice when things are connected in surprising ways. So if we go over to Agda, then we see that we can also convince Agda of this. So here I have category C and D, functors f and g between them, and I'm assuming I have an adjunction. Now I'm going to make a monad, and I'm going to make the underlying functor to be the composition of f and g, like that. And here I needed the return. So I said that if I looked at 2 of the identity, I always get the wrong category, then that goes from x to g of f of x. It's a little bit hard to read, but for any x, we go from x to g of f of x. So that's what we want. Okay, and the fact that this is natural now follows from the fact that to and from was supposed to be natural, right? So this is why we needed this, in fact, just to make this work. And for the join, we said we should apply g to something, so we'll do f map of g, and then we wanted from of the other identity, so it's going to be in C then. Okay, and I prepared this before. It's a little bit more involved why this is natural, but again, it follows from the fact that from is natural, right? And some category laws. And from was natural if 2 was natural. We had it up here, right? You could prove that from the fact that 2 was natural. Okay, and then we also have the monad laws, but these again follow from the fact that 2 is natural and that from and to are inverses. So that's the same for all of these. From is natural, and that's it for that one, I think. And here, from is natural, and from is natural. That's all we need. Okay, so that's the amazing fact. If you have an adjunction, then you get a monad for free. And often these monads are something sensible, right? So for example, there is a monad which gives us the smallest, a way to turn a set into a monoid, and if you look at the corresponding adjunction, that gives you the list monad. So that's where lists come from the fact that you can make monoids out of sets, which is not at all obvious.